Hi, welcome back to my channel. My name is Gina. In the previous two lectures, we talked about determinants and effect of elementary row operations on determinants. If you haven't watched them, I'll put the link up there. Today we are going to continue to talk about determinants. It will be easier to use cofactor expansion if we can have a row or a column that has a lot of zeros. And to get that, we can do row operations or column operations. And the fact that we can use column operation comes from this theorem. The theorem says determinant of a transpose of a matrix equals to determinant of the matrix. So the determinant of a transpose remains the same. Here's a generalized 2x2 determinant, A, B, C, and D. Its determinant is A times D minus B times C. And from the theorem, it should equal to the determinant of its transpose, which is A, C, B, and D. This equals A times D minus C times B, which equals to the original determinant. And this is an important result because it says everything that we stated about rows are also true for columns. For example, in the previous video, we said when we interchange two rows, the determinant will change the sign. Similarly, if we interchange two columns, its determinant will also have an opposite sign. So we can also perform column operations. We can replace a column by a scalar multiple of itself, or we can add a scalar multiple of a column to another column. But you have to be careful that we can only perform the column operations when we are computing the determinants, and never when we are solving a linear system. Let's look at two examples. In this example, we have a 3x3 determinant. So we want to use cofactor expansion as well as row and column operations. When we use the cofactor expansion, it is more efficient if we have a row or a column that has many zeros. It is most efficient when we only have an entry that is non-zero. So we can use row or column operations to make the other entries zero. For example, in this matrix, in the second row, I have a 0, and I also have a positive 1. So let's keep the positive 1, and let's try to make the other entries along the second row 0. So I want to eliminate this 3. Then this determinant equals, if I replace column 1 by column 1 minus 3 times column 2. This is the third type of the elementary row operation or column operation. So the determinant is the same. That is why I have the equal sign here. Then this determinant equals, first column I have 1 plus 3, that is 4. Then 3 minus 3 is 0, and 2 plus 3, that is 5. The other two columns remain the same. Negative 1, 1, negative 1, 2, 0, and 3. Then I can use the cofactor expansion along row 2. The only non-zero entry is the 1. So if I do cofactor expansion, the 1 is in the second row and second column. So its cofactor will have a sign of positive, since 2 plus 2 is an even number. So I have the entry 1 times positive of the determinant of the minor matrix by deleting the second row and second column. The 4 entries are left are 4, 2, 5, and 3, which equals 1 times the determinant, 4 times 3 minus 2 times 5. So the determinant of this matrix is 2. Now let's look at the second example. Here we have a 4x4 determinant. Again, we are going to pick the row or the column that has more zero entries. Here I see there are 2 zeros along the first column, and there's also a 1 in the fourth row. So I'm going to keep this 1, and I'll eliminate the other entries along the first column. Then I can replace row 1 by row 1 minus 2 times row 4. to eliminate this 2. Then the determinant becomes 0, then 3 minus 2 is 1, 0 minus 4 is negative 4, and 1 minus 10, that is negative 9. And the other 3 rows remain the same. 0, 1, negative 1, 3, 0, 5, 1, and 1. And last row is 1, 1, 2, and 5. Now I can do the cofactor expansion along the first column. The only non-zero entry is the 1 here. So 1 times its cofactor. The entry is in the 4th row and first column. Sum of 4 and 1 is odd, so I will have a negative sign. Then times the determinant of the minor matrix after we delete the 4th row and the first column. So we are left with 1, negative 4, negative 9, 1, negative 1, 3, and 5, 1, and 1. Now I have a 3 by 3 determinant. Again, I'm going to look for the row or the column that has the most 0 entries. However, there's no 0 entries here. So I'll just pick a 1. For example, I can keep this 1. And I want to do cofactor expansion along the row. So I'm going to eliminate the 5 and the 1. Then this equals. I'm going to replace column 1 by column 1 minus 5 times column 3. And replace column 2 by column 2 minus column 3. Then this becomes, remember the negative sign in front? Column 1 is now 1 plus 45, that is 44. Then 1 minus 15, that is negative 14. And 5 minus 5, that is 0. Second column we have negative 4 plus 9, that is 5. Then negative 1 minus 3, that is negative 4. And 1 minus 1, that is 0. And the third column remains the same. Negative 9, 3, and 1. So now in the third row, this 1 is the only non-zero entry. Then it will be more efficient to do column expansion along the third row. So this equals the negative sign in front and times the entry 1. And this entry is in the third row and third column. Sum of 3 and 3 is even, so we'll have a positive sign. Then times the determinant of the minor matrix by deleting the third row and the third column. And we are left with 44, 5, negative 14, and negative 4. So this equals negative of 44 times negative 4, that is negative 176, and minus 5 times negative 14, that is plus 70. So the determinant of this 4 by 4 matrix is 106. And that is the end of the lecture. If you are interested in the complete course of my linear algebra course, I'll put the link down below. If you like my videos, please like and subscribe, and I'll see you in the next video.